Okay, so in this video we're going to start talking about thermodynamics. Now the first thing that we need to know is figure out the work done in any thermodynamics process. Okay, our goal is once we get the work done, we'll talk about some internal energy changes, and then we will come up with our first law of thermodynamics. Alright, so let us consider a process. So let's say you have a gas that is enclosed in a cylinder, and there is a piston that is free to move in the cylinder. Okay, and what we are going to do is we're going to exert some we're going to compress this gas under a constant pressure of value P. Okay, so let's say that the piston goes down some amount of some height delta Y. Okay, and in doing so it has been compressed. So the area is A, we're exerting some pressure P, and the whole thing is getting compressed. So what we realize that if we measure all heights on the bottom here, okay, then the work done is equal to F, we'll use our equation FD cosine theta. Since the pressure is constant, the force will be constant, and the force itself is P times A, and D in this case is delta Y, and we have a cosine of 180. Okay, the reason we write cosine 180 is because we're going to measure y from the bottom here, so the angle is 180. Okay, and so we end up getting negative P times A times delta Y. Alright, now A times delta Y, you see, is nothing but the volume, so it's negative P delta V, and this is under constant pressure. This is when the pressure is fixed. So under constant pressure, the work done is given by negative P delta V. Okay. Now understand, if the gas is compressed, okay, delta V ends up being negative, and which means W ends up being positive. Now if the gas expands, then delta V is positive and W is negative. Okay, now when the work done is positive, okay, this W that we said, we say that the work is done on the gas, and when W is negative, we say that the work is done by the gas. So this convention is very important, and most of the times the questions, when we ask the question about, hey, what is the work done, okay, we typically mean work done on the gas, and in case they say work done by the gas, then you need to keep track of the signs correctly. It's very simple. Remember, if the gas expands, work done is positive. If the gas compresses, if the gas expands, the work done on the gas is positive. If the gas, I think I just repeated the same mistake again. If the gas expands, the work done on the gas is negative. And if the gas compresses, work done on the gas is positive. Okay, great. So that's where we are. Okay, also now, what if the P is not constant? What if P is varying? What happens? Okay, so when P is varying, we need to be a little more careful, and the concept is very simple. If we have PV and if P is changing, okay, then once again what we'll do is the work done will be the area enclosed by this area under the curve, and the area enclosed by the curve and the x-axis. Okay, so for these cases the work done will be equal to plus or minus the area enclosed by the curve, not enclosed, the area under the curve, under the PV curve. Okay, now once again you see that I am putting the plus or minus here, and this implies basically again we'll have to follow our rules. Okay, so depending on the process, it'll be positive or negative. So if volume increases, okay, W is going to be negative. If the volume decreases, then W is going to be positive. So in fact, in the process that I have shown here, clearly the volume is increasing, so the work done in this process is going to be negative. So this will be negative W. Okay, I should write W is negative here. Okay, and on the other hand, if I have P versus V, and if the process is simply the opposite direction, okay, then once again we find the work done by finding the area, but in this case W is positive. So keep this in mind. It's very simple to keep in mind, keep track of. Okay, alright, so let us apply this concept to a couple of simple situations. So first example will be in the form. We'll just take the example that we just had. So let us say we have a process in which the volume goes from V0 to 3V0 and the pressure goes from P0 to 3P0. Okay, and let us say that the gas expands, okay, in this manner. Then we're going to ask what is the work done. Okay, so I would recommend at this point just pause the video, calculate this work done by yourself, and then restart it and see, verify your answer. Okay, and when you do this, you have to be careful of the sign and all those things. So make sure that you follow the conventions properly. Okay, so I'm going to move on with the solution at this point. Okay, so the work done is again the area under the curve. So what I'll do is I'll find the area, all this area. Now it's a trapezoid. So I'm going to use my equation for the formula for the trapezoid. It will be equal to sum of the half times the sum of the parallel sides. In this case, the parallel sides are P0 plus 3B0 and multiplied by the distance between the parallel sides, which happens to be 2 times V0. Okay, if you're uncomfortable doing that, break it up into a triangle and a rectangle, and you should end up getting the same answer as I have. So the first time here becomes 4P0, so it'll be half times 4P0 times 2V0. When we simplify it, we end up getting 4P0 V0. So this is the work done. Now, I kind of ignored one important point here. We need to worry about the sign. Now clearly here, the gas is expanding. So the work done on the gas is all going to be negative. So we need to put a negative sign everywhere. Okay, so that was my mistake. Make sure you fix that. Alright, great. So that's one problem. Okay, here's another problem. Let's look at this process. Let's say that the gas goes from pressure P0 to pressure 3P0. Okay, once again PV graph. What is the work done in this case? Once again, pause, write the answer down, and we'll verify. Okay, and all this is happening at some volume V0. Okay, alright, so let's assume that you did all this. Now let's write the answer down, and the answer to this one is that the work done is equal to 0. Okay, because the volume is not changing, since V is equal to some constant. If the volume remains fixed, the work done will be 0. Great, so we know how to find the work done for some of these processes. Okay, let's look at one more problem, and this is something that we'll be coming across a lot. Let us find the work done in a cycle. Okay, and by cycle we mean that we take our gas and we take it through various steps and we bring it back to whatever it started with. Okay, for example, a cycle would be let's say that I start with, say, some volume V0, some pressure P0. I take it to this new volume, new pressure of 3P0, new volume of 3V0, then bring it back to, so let's say we start at A, go to B, go to C, and then back to A. So this is a cycle. Okay, cycle. Great. So let us figure out how to find the work done for a cycle. First, let's go through the process that we already know. Okay, we'll break the cycle into 3 pieces. First will be WAB. To find the work for WAB, we'll find the area that is under AB and enclosed by AB, this vertical line here, this other vertical line, and also the part of the x-axis. Okay, so the work done will be negative. We have already made this calculation. So it will be negative because the volume is increasing. Half times P0 plus 3P0 times 2V0. It ends up being equal to negative 4P0 V0. Okay, great. Now let's find the work done for the second process, which is BC. If you look at BC, BC is a process at a constant volume. And the volume is constant, then the work done is going to be equal to 0. So that's easy. Let's do the same thing for the third process, VWCA. Now to find the work done for the third process, okay, we see that the volume is decreasing, so we know it's going to be positive, and it's simply, the area under this last part, which is this part out here, which is simply the area of a rectangle. Okay, and that's going to be equal to the height P0 times 2V0, and it'll end up being equal to what's the word? It's 2P0 V0. Okay, so now the work done for the entire cycle, we can represent a cycle with a circle with a dot in it. For the entire cycle, the work done is equal to negative 4 POVO plus 0 plus 2 POVO, and this would be equal to negative 2 POVO. Okay, so we can do this the long way, but there is a quicker way to do this, okay, to obtain this final answer. Alright, and in order to do this, okay, if you look at this diagram, okay, I'm going to redraw this again. And what we have is we have the pressure here, the volume here, the pressure goes from here to here and here and here. Okay, so I'm going to use colors to represent all the areas. Okay, so for process A to B, the area that we had was all this entire area, the entire area of the trapezoid. For B to C, we didn't really have anything, but for C to A, okay, we had this area. Okay, and you see that the first blue area, the blue shaded area, is all negative. The red shaded area is positive, and they cancel each other out. And essentially, we are left with the green area. So I'm going to show, I don't know what I'm going to show. Okay, vertical lines will be the green area. Okay, and that you see is simply the area enclosed by this curve. Okay, so for a cycle, so work done for a cycle is equal to plus or minus area enclosed by the cycle. Okay, and again, the way we decide the positive or negative sign is that if it's a clockwise cycle, okay, it'll be negative. For a counterclockwise cycle, it'll be positive. And once again, I really don't recommend trying to memorize clockwise negative, counterclockwise positive. What you can do is, if you look at the process, if you look at this process again here, during the process A to B, okay, which is, the most amount of work was done, and that work was clearly negative because the volume was increasing. Okay, so we know that the total work done for the cycle has to be negative. Okay, on the other hand, if we had a counterclockwise cycle like so, let's say something went, in a cycle like this, and this was counterclockwise, then we know that the most amount of work done was for this part of the cycle. Okay, all this work, and it's clearly positive. So the net work done will have to be positive. Okay, so this is basically finding the work done in all the cycles, work done for individual processes. Okay, remember the work done when the volume is constant is 0. And essentially the work done for a cycle is equal to the area enclosed by the cycle. Okay, and we have to put appropriate signs. If the gas expands, the work done is positive. What am I saying? If the gas expands, work done on the gas is negative. If the gas compresses, the work done on the gas is positive. And instead, if we were asking for the work done by the gas, then it's simply the opposite of the answer. Okay, work done by the gas during an expansion is positive, and during a compression is negative. Okay, so keep those things in mind, and that'll help you in the next part. Great.